Welcome again to 168. If it's your first time attending, my name is Vinay Goyal, and our TA is Leonardo, and we're both going to try to make the best to help you succeed. That's the goal here. The first question I have is, what is finite elements? Somebody very succinctly tell me what is finite elements in a very complete sentence. I want a very complete sentence of what is finite elements. And I appreciate the attempt. That's what I'm looking for.
Breaking a problem into very small, definite, solvable pieces in order to determine the whole.
And so she's contributed significantly here. Can somebody add more to that sentence?
So it's a strategic way to solve partial differential equations with dividing into the small elements.
So let's combine the two definitions here. And finite elements is a systematic approach that allows you to solve partial differential equations for a complicated domain. It can be complicated loads or boundary conditions by using discretization of that complicated domain into simpler subdomains called elements connected to each other by nodes, and allows you to then take the partial differential equation and turn it into a system of algebraic equations that can be solved, usually linear, but if it's a nonlinear problem, hopefully we'll get to that at some point in this class. Does that make sense? How many of you have started the homework? Okay, so for the rest of you, you want to start now, okay, because so tomorrow there's discussion class, and maybe there's questions there, and things will start piling up. They'll be piling up really quickly. And so my advice to you at this top-notch university is to really crank it up every day. Put some amount of time every day. Because what I explain here, right, is going to go through one ear and go out through the other one. So I'm putting the effort to teach you the concepts, and what I'd like you to do is, after the class, spend some time trying to review the materials. This particular presentation has over 55 pages or more, I believe. And so the next one today has another 60. And next Tuesday is another 60. And all these lectures will be very dense and you're going to have to pay a lot of attention, okay? And so for that reason, I really recommend that you get started immediately. Every single of these homeworks, okay? And every single one of these homeworks has a very particular trick that I put in there on purpose to try to drive a concept home, okay? And so for that reason, I think you should start also a little bit early. And I'm giving you all the tools that you need in this PowerPoint also. In addition, I really appreciate many of you have contacted me through email, but in addition to emailing me, please copy Leonardo so he's aware of the questions that are coming up. So that way, I've been responding to a lot of them, but at the same time, he can also respond as necessary, okay? And also, I encourage, if you have a question, post it in the forum, and post also the answer that was given by us, so everybody can benefit from the question and the answer. It will be very difficult for me to take every question and put the answer in the forum, but if you can help with that, as a team, we can help each other as well. Okay? Well, thank you very much for listening to this short sermon that I gave you, but I really need you to get started. So let's look at how we will implement such methodology in Abaqus. You can do it really by hand, really quick, and you can see here I took this two-spring system. I've randomly put some numbers in here. So this number, no number, I call it 5. This one 6. This 7. This element number, I call it 10. This one 11. And look how easy. It's very short. But if you learn the lingo now, it's going to come very long ways when you move on later in industry. Because using the GUI is great. But I will tell you that the GUI can be a black box. And so looking at the input file and trying to understand how this connects to when you do things by hand also will be of great value to you. So as you can see, the first section here, you define a node. You define a node number, you put the node number there, and you can see I put 5, 6, and 7. That's 5, 6, and 7 right there. And what I've done next, I put the coordinates, x, y, x and y. Okay, in 3D it will be x, y, and z. And then next, what I have is the element definition. Now, each of these, you see the star element, star node, these are keywords that you can actually find in the Abaqus documentation. So if you go to the Abaqus documentation, how many of you have downloaded Abaqus already? Very, very good. So the rest of you, it's time for you to download that as well. It will come with documentation, and that documentation, in the keyword section, you can find what star node means, what star element means. When you see 2 stars at the beginning, this means comments. So you can write anything you want. You can say, this class is hard. You can do that too. Okay? You can use that section to comment. So the element type I'm using is Spring2, and Spring2, what that does, it connects 2 nodes. So that's what I've used, Spring2. And Abaqus manual is really, really good. You can actually learn a lot just by looking at it. There's a verification manual, there's a benchwork manual, there's examples that they give you. There's actually people that have posted in YouTube many different examples of their own. So you can actually even learn. If you don't like Leonardo, you can actually go to YouTube and somebody out there posted a tutorial on how to do something, okay? But I think you're going to like him very much because I like him very much. So now you have element 10. Element 10 connects nodes 5 and 6. This is called connectivity, right? So these are connectivity metrics. This connects the element. That's the element number, and these are the nodes that go along with that. For element 11, what is the connectivity for the nodes? 6 and 7. So that's what you see there, 6 and 7. Okay? And then finally, in Abaqus, if you look at the manual, it says, okay, start Spring to define the stiffness. And you see here 1, that just means that you're looking at degree of freedom 1. So since this is uniaxial, everything is in one direction. So that's why you see that 1 and 1 there. And then finally, here's where the solution starts. That's where you invoke the solution. And we're looking at static solution. The boundary conditions are that the left-hand side is fixed. So node number 5 is fixed. And it's fixed. I put all degrees of freedom fixed, 1 through 6. But in reality, it's a 1D problem, so it's just the 1 degree of freedom that's fixed. So you could also put 1 through 1. And then star C load is a concentrated load. You can apply a concentrated load. That's applied to node number 7, degree of freedom number 1. And that's the amount of load I applied, 10. And if you look, we get the solution here. And if you do a hand calculation to get the deflections measured here and here, which are given here, the values are provided here, you will see that it matches your hand calculation. It's going to match. Okay. Does that make sense, everybody? Just a really quick synopsis. If you have additional questions, Leonardo will go a lot deeper into it. Okay. Both the GUI, hopefully we'll capture how to do it in GUI and also by hand. In your homework, the one I gave you, you also have to do it by hand. I want you to do all that by hand to create that input file by hand. Okay. So that's the goal. Let's tackle a case that I did not cover. I think I need to cover a little bit again so that it's much more clear, because problem number 2 of the first homework deals with this. And I want to make sure that's very clear how we have to deal with this particular problem. So let's look at a special case where you apply constraints that are non-zero. I kind of covered that last month, Tuesday. But today I'm going to go a tad bit deeper, not a lot more deeper, but just a little bit more. So the original example I have given was a 3-spring system fixed on the left, so G equals 0. So the amount of deflection I'm applying is G equals 0. And on the right-hand side is a load applied P. Okay, so that was the original system. And we talked about that when there's a 0 constraint, just make the code number 0 and 0, right? That's what we talked about. And these are the degrees of freedom that are left, 1 and 2. Okay? That was the original example, and we solved that. And we manufactured the code number matrix. And element 1 is 0 and 2, right? Sorry, 0 and 2. Element 2 is 0 and 1. And then element 3 is 1 and 2. So we devise that. For the original example, we finish it up. We did all the work for the assembly. But for the modified example, the one I want to give today, so that you're able to do your homework, problem number 2, more intelligently, is that let's say that this is a non-zero applied deflection. So apply 1 inch or ½ inch. In that scenario, what I recommend that you should do is don't make it 0. Make it 1 and 1. So make it don't put 0 for the constraint. Just put 1 there for that particular degree of freedom. And then just number the rest of it, 2 and 3, right? So my code number now is for element 1 is 1 and 3. For element 2 is 1 and 2. Is that correct? Is everybody tracking? Yeah? For element 3, then I have 2 and 3. That's the code number. And so now the deflection or the displacement vector is basically G, which is known. This is like 1 inch, ½ inch, okay? D1 and D2. So what you do now is you're going to assemble it this way, using this procedure. So you go and assemble it, and you can see now I got a 3 by 3 matrix. Before, in the original example, I had a 2 by 2, okay? But in this example, I have a 3 by 3 because now I'm including the non-zero constraint in here. That becomes important because what I want you to do is to be able to go back to the matrix here. The whole K is known. That's all known. What is the only unknowns here? Somebody. Sorry? D1 and D2. Those are the unknowns. But G is known. And since G is known, that there must be a reaction force. There's no load applied on degree of freedom 2. And on degree of freedom 2, there's a load applied P. Okay? So all you have to do now is to use the procedure I discussed in the previous lecture to solve for D1 and D2. Okay? You can do it by hand, so you can actually solve the last 2 equations for D1 and D2, and then basically solve for the reaction force. But this is the automated process to do that, if you wanted to do it with matrix notation. Okay? Any questions there? I already covered this before, okay? But I'm covering a little bit deeper because I think you're going to need that for problem number 2. Okay?
Just the non-zero constraint, is that just for, like, is there some practicality to that, or is that just to learn?
No, you can have situations like that. So say you have a heat transfer problem. In a heat transfer problem, I could apply a temperature. Well, that temperature is not a non-zero value, right? In structural mechanics, most of the loads are applied, but you don't apply displacements. They're usually fixed boundary conditions and things like that. But for other problems, I think it's important for us to learn these concepts. Does that make sense? Okay, so just to make sure for the video, the question was, is there any practicality to solving this problem? The answer is yes. In structural mechanics, for my area of expertise, I've also applied displacement for several problems. It will take me a long time to discuss each of them, but there is a lot of practicality here. Okay, I'm going to try to make the class practical. The homework, of course, in some sense is also practical because you'll try to discretize the domain for several different problems, right? But I'm not going to give you a rocket or an aircraft to solve because it will take a long period of time. But I hope that at some point we can get a CAD model of a part, and then we can mesh it and do that kind of thing. So I think that will happen down the road, hopefully. All right, so that's end page for Springs. Today I'm going to transition to trusses. And then next week I'm going to transition, hopefully, to a strong form Galerkin. That's the next topic coming up. Okay. So let's tackle trusses today. And any questions? Any thoughts? Anybody wants to contribute? I also welcome people that want to contribute from industry. If you're from industry and you want to give a lesson learned about something you did wrong in finite elements, let's share that so that everybody else can learn that experience. Okay. So that could be a good thing. Today I found an error in a model where the coefficient of thermal expansion was per degree C, right, centigrades. But then the temperatures that were being used were in a different temperature, like Kelvin or Fahrenheit. So we need to pay attention to that. Some people don't pay attention to that, okay? Let's look at a truss analysis example. So for fine elements. So a truss, in general, you've seen trusses, and this is not just strictly for civil engineering. Trusses also show up in a lot of applications with launch vehicles, spacecraft, and other things like that. So I show a civil engineering structure because it's typical and it's easy to show. But if I look at a connection in a truss system, typically you will have a gusset plate, and you have members that are connected like that. Okay, and in general, these connections use large bolts or large pins, but we're going to idealize that. And you may have learned this in mechanics of materials, so this may be a repetition. But we'll idealize that connection as a frictionless pin. And that way, now the system now behaves like a two-force member. It does not take any bending. And no moments will be transmitted through a pin. Okay? Later on, we may be able to cover frames which will be able to carry bending through the connections. The weights of the members are typically neglected, and trusses now become a two-force member, meaning that the forces carried by each truss is only along the axis of the length of the truss. Does that make sense? It can only take load along the length of that truss. Okay. From that perspective, if I look at the assumptions, now basically you have a two-force member. Each truss can either take compression, it can take tension, it can take compression, as you see there, but it will be only along the length of the truss. Does that make sense, everybody? Yes? Okay, so with that in mind, the strategy we're going to use with trusses is the following. Step one is to idealize a truss structure to be discretized into elements. So that will be the first step. The second step, we're going to discretize the behavior of a local element because that's what we talked about. We talked about the first step is discretizing the domain. The second step is to approximate the behavior over a general element, right? And then the third is to assemble the system together. And you already have learned a little bit how to assemble things, and today we'll talk about that as well. And number four, we'll then apply the boundary conditions, and then we'll apply the loads, and then solve a system of algebraic system of equations. Okay, algebraic systems of equations. So let's look at this example. This example is a truss system, and it's fixed here at the bottom. It's fixed here at the bottom here, and what you have here is element numbers being shown 1, 2, 3, 4, 5, 6, 7. But in general, this is a truss system I'm giving you, and we're going to discretize it by calling out the element numbers. That's 1, that's 2, that's 3, and so forth. Let's see. So in the next slide, I think there's a yeah. So let's continue here. So if I take one truss member and I try to understand its element behavior, okay, I already know that truss can only take loads along the length of the truss. And for that reason, I'll look at it. And that's how this element behavior, at least the diagram for this element will look like. This node could move amount di, this node could move to the right and amount dj, and correspondingly there will be a load applied, internal load acting on this part. That's balancing the external forces being applied. So at the local element, you're trying to develop the element, we call it the element formulation. So anytime I talk about developing the behavior of a local element, This is called an element formulation, formulating how an element, a general element behaves. Because the idea in finite elements is if I can generalize the behavior of an element, I can now, I basically know the general behavior of any other element that has the same shape. That's the whole point of finite elements. It simplifies life, okay? It simplifies the process. So if I look at the stress acting on this bar, that's P over A. If I look at the strain is basically the relative deflection, dj minus di divided by the original length. Everybody knows this formula. Changing length divided by L, basically. And so you know that stress is related to strain through what? Hooke's law. Stress equals E times epsilon. How do I know this relationship? Stress related to strain. How do I find this relationship? I have to perform an experiment. I have to use an instrument machine and load up the sample in tension, right? So that's how I calculate E, right? Or if it's aluminum and I tell you the grade of aluminum, what will you do? You look it up in a handbook. In a materials handbook for the particular grade of material you're looking at. You can also use Google, but you also want to, in industry, in real life, you want to really look at the particular grade of material you're working on, okay? And so now I have calculated the relationship of stress to strain through Hooke's law, and that's how the formula looks. P over A equals E over L dj di. And so now if I bring A to the other side of the equation, I get EA over L. That's basically spring stiffness. And I get what I had shown you on Tuesday, is a stiffness matrix for a general a bar element. But this is the problem. This is the problem with this. The problem with this is that I have bars oriented in different directions. That's the problem. So maybe that formula that works very well for the bar that's horizontal. But if I have bars oriented in other directions, how do I deal with that? Because the idea in finite elements is to be able to have a systematic approach. And so I want to have global deflections that are pointed, basically this is my X coordinate system, this is a Y coordinate system. I want everything to be referenced to that coordinate system. I don't want to have a bunch of local coordinate systems. I want to be able to relate that local coordinate system to the global coordinate system and still be able to solve the problem efficiently. Does that make sense? Yes? Okay, great. So what I'm going to do, and don't go, it's easy to get freaked out with math, but if you take your time to be patient, you'll follow it. Okay, that's really the goal here. So I'm going to attempt to use this for the first time. We'll see how this goes. Pen on. Good. All right. You're not going to see my face for a little while. I don't think this is good, whatever happened. Okay. All right. So if I look at a regular element, which is this one here, let's see if this writes. I don't know what that's coming up. Okay. This methodology is not working for me right now. So that's okay. We'll continue. Old school. Old school. All right. So if I look at the local element behavior, that's a local system. Okay, that's a local system. If I look at how much the deflection will be for this node, it's going to move some amount to the right. Okay, so let's call that del jx. What I really wanted to do, I want to represent that in the global coordinate system. How do I do that? Well, that can be represented, if I know the angle beta, I can then break up this into two vectors, this one and this one, right? So I can project this del jx into x and to y by using the cosine of beta. Does that make sense? Yes? Okay. And then now I look at this contribution here, this del jy. And again, I can do the same thing. That del jy is this one here. I can now project that into the x-axis and y-axis, right? And so if I can do that, now what I need to do is relate this. So that's a contribution of del Jx and del Jy. I have to relate this now to the global system. Let's say the global system, the deflection is dJx and dJy. Okay, so tell me how I calculate dJx then. I just summed the two. So I just add this contribution from del Jx, and I add it up to this contribution from del Jy. You see that? So that's where the minus sign is coming up here, right? So that's for x. What about for y? Same thing. I take the vertical contributions, del Jx sine beta, and add it up to this one here, del Jy cosine beta. They're additive in this case. Both of them are acting, you know, in this direction. So these two can be added together additively. Okay? Is that making sense, guys? So that's how I can relate the deflection in the local coordinate system, because this is a local coordinate system. This is perpendicular to the bar, that's parallel to the bar. That's how I am relating that to the global deflections, because this was really useful to me, is to know the global deflections for the system of interest. Okay? Does that make sense? Okay, let's continue here. I'm going to basically put it in a matrix notation. Okay, so can you see the mouse when I move it? Okay, so this here is what I derived just right now. Okay, and so can you see that this can be written in matrix notation this way? Yeah. Now I did that for node J. I did that for node J. I can repeat the same thing for node I, which is here at the bottom, right? We're deriving the element formulation that can be used for any element. That's what we're trying to do here. And so, so if I need to repeat it, what I can do, since it's the same thing for I, all you have to do is construct a transformation matrix that connects the deflections on one end, on node I, x and y, and node J, x and y. And you can see here that if I multiply this together with that, I should be able to get dix, diy, djx, and djy. Do you see that with me? I'll give you a couple of seconds to kind of look over this, so I'm not rushing it. And then ask me if you have questions still. Can you see that when I multiply this times that, I will get this, and I also get the same thing, but for the I node, for the node, the other node. Yes? Any questions? Any questions? No questions? Okay. So now I have related the deflections in the global coordinate system for that element to the local coordinate system through a transformation matrix. Okay. For 10 points extra credit, I want you to show that the inverse of this matrix is equal to the transpose. Okay. That's usually the case for transformation matrices. But I want you to actually go ahead and show that. You can use MATLAB, you can use Mathematica, whatever software you want. Or you can do it by hand. More power to you, whatever you want to use. But if you want to get extra credit, I would like to see that calculation. Okay, so now I have a way of relating the local deflections to the global deflections. Okay? And the local deflections are acting how? Somebody tell me. How are these local deflections acting? Sorry, speak louder. Yeah, very good. So these local deflections are acting along the truss. That's del Gx and del Ix. Those two are acting along the truss. And then these two are acting perpendicular to the truss. And I am basically transforming this to a global coordinate system. Okay? So let's look at what we've done. So right here, del Jx and del Jy, del Jx is acting along the truss system. And del jy is acting perpendicular to the truss system. And what we've done is we transform that so that so we have this. So it's in the global coordinate system, the letter D there, djy and djx. Does that make sense? We can do the same thing with the force. So the local forces, which have small f, I'm using small f for local force of the element, can also be transformed to a global force system. Okay? And if I do that, I can use the same equation. The same equation I just used for deflections, I can use it for the forces. I can transform these guys in the same way. Just like the deflections, these forces, Fix, acts along the truss member. You understand? And Fjx acts here, along the truss axis. Now let's look at the Fiy and Fjy. Any guesses on what that is for a bar? If a bar can only take loads along the length of the truss, then perpendicular to the truss, what is it? 0. So these guys are going to be 0, and you're going to see that in the examples I'll give you. But we need to keep that there because I need to multiply this to my transformation matrix, which then converts it into global force quantity. Sorry, not a global force quantity. It's a local force quantity, but local to the element, but in the global frame, using the global coordinate system, which is x and y, right? Now, I already asked you for 10 points extra credit to demonstrate that T inverse equals T transpose. And so for that reason, what I can do, if I wanted to, I can take, in this equation, you see this D equals T del, right? If I want to invert this, I want to solve for del, what will you do? Pre-multiply by T inverse, what do I get here? Identity matrix. And now I have T inverse times D. What is T inverse? T transpose. So that's what I have I found here. I found that del, I can solve it, is T transpose times D. Okay? It will become apparent why that's actually powerful. Now, for the force, I can do the same thing. I can solve for force by pre-multiplying T inverse here and T inverse here. And then I find that this identity matrix, and what is T inverse? T transpose again. Okay? Hey, pay attention, guys. You're falling asleep. It's okay. I'm just waking you up. So, small f equals T transpose times F. And F is in the local coordinate system, and this is in the global coordinate system. Okay? But these are local quantities. We're looking at local element behavior. Now, I'm not done yet. I have a lot of work to do still. And so if I look at the at a typical a bar truss, we already derived this equation, remember? So these equations should be the equation for this bar. There's no transverse force, but we know that this should be the relationship. We derived it just a minute ago again. That should be a relationship for that. But I'm going to trick the system. What I'm going to do, I'm going to add a rows of zeros here and a rows of zeros here, and those correspond to the transverse quantities. The quantities, they're not here, because these quantities are along the truss, but I want to get some quantities across or transverse, perpendicular to the truss, and to do that, I'm adding rows of zeros. You see what I'm saying? So I'm adding rows of zeros, and as a consequence, I have to add rows of columns of zeros. And so if I multiply this times that, I should technically get this back. You agree? Yes? Okay, I need to hear yes so I know that you understood it. All right, do you understand it? Very good. So what I'm going to do now, I'm going to say force. You agree that force equals TF. You agree with that? Yes? Yeah. Okay. So if force equals TF, then I can now substitute what F is. Small f equals K, the local stiffness matrix, okay, which is this one right here, sorry, times del. So that's what this is. So all I did is substitute what small f is. Now, earlier, I don't even remember, but I solved for del earlier in terms of big D, and I got that, remember? Yes? So I'll put that in here, And now guess what? Now I got an equation that is local to the element, but it uses global coordinate systems to describe that force, and then it uses global coordinate systems to describe that deflection, which now everything is acting in a global coordinate system, x and y. Does that make sense, what we've done? So now what I've done really is, now all I have to do from now on is to calculate this stiffness matrix and then calculate these t's. And I already gave you the formula for t. One of the things I want to teach you in this class is very important for you to trust the system. What I mean with that is that if you follow the steps, that's what matters. Don't, even if you ask me, hey, Vinay, do you remember what t is? I'm not going to remember it. But what's important is that you stored it somewhere and you have it written. So I can go back and say, I have t. I calculated t already. This is t. That's t. Okay? So try to pollute your mind with information that's necessary. Because this class, that's what computers are for. They're there to track all these matrices. And that's what finite elements is about. Finite elements is about coming up with an approach so that the computer can take care of it. So don't feel like you have to know, you have to know the steps on how we derived it, because that's what this class is about. But what I want to make sure is that you are not stressing yourself out, okay? Because if you stress yourself out, you will not learn, okay? So that's what's important right here for you to understand. That we come up with the with the element formulation that works by referring the quantities to a global coordinate system, because that's what trusses have, orientations that are not straight. They're different orientations. So let's move on here and look at what that calculation looks like. I already gave you what t is earlier. I know what k prime is this here, and then I have t transpose. If I multiply all that out, this is what you're going to get. You can get a symmetric stiffness matrix. It's no surprise. You get a symmetric stiffness matrix. When you see C there, that's cosine beta, and then when you see S, it's sine beta. Okay. What's important for you to also remember is how that beta is measured. Beta, in the way we've defined it, starts from the x-axis, measured from here, this x-axis, moving counterclockwise. Okay. So that's what's important for you to kind of keep in mind. That's important because when you develop an element formulation, you have to keep track of how you develop the element. Okay? You cannot arbitrarily make up a convention and then switch it later. You have to keep track of that. So now I know how to calculate a stiffness matrix. And the question is, hey, how do I apply this? Well, that's what we have examples for, is to go through that process. The same process for assembly, we already have the element formulation here. Everything is in global, isn't that nice? Everything is global coordinate system. And I have the local element formulation, I have the stiffness matrix, and now I will have, for every element, I will have 4 code numbers now that I have to track, not 2 like before. Okay, so you have to keep track of that. In this example, so the summary of this example is basically we discretize the body, we develop the local element behavior, okay, and then we'll use code numbers to assemble things together. And I'll give you an example. Hopefully that example will be of help. So example number 1. Example number 1 has a truss system as described on the left-hand side. And you can see here that you have a truss here, truss there. This one is pinned, and this one is a roller. Okay, so it's kind of free to move vertically. Then I apply a load of 45 degrees, P naught. Okay, so if I look at this problem, I can discretize the domain, and I'll discretize into 3 elements. And I'll assign element number 1 to be this guy, element number 2 to be this guy, element number 3 to be that guy. The second step, I want to define what beta is for that truss. Because remember, beta, how does beta become important? How? I'm going to knit it, right? Yeah, exactly. For beta is needed to relate local to global. and it's part of that formula that I showed you earlier here. So that's required here in this formula, cosine of beta, sine of beta. And so for element number 1, do you agree that beta is 0? If I measure, that's the origin for that element. Let's look at element number 2. For element number 2, I have two options. I have two options for element number 2. For element number 2, I can go from this node down or from this node down. Okay? I arbitrarily chose that that node starts from top to bottom. That's fine. I can do that. But when I calculate beta, I have to be careful. So the beta should be calculated against the x-axis along, and I'm going from left to right. That's how I decided for this example problem. And so what is that angle? Now it's minus 45 degrees. And you know it's minus 45. You know that angle because you know that this is L and this is L, so you know the angles. That's geometry. Okay, that's geometry. And then for element 3, I'm going from, I chose it arbitrarily. You can go from top to bottom or bottom to top, but I went from bottom to top. So I to J, and then I calculate against the I, or the I is your origin. So then what is that angle? 90 degrees. Okay? Any questions? Any questions? So as an example for element 2, all I have to do is plug it into my formula for K. That's all I have to do. Okay? Let's look at the code numbers. Is this constrained, right? Fully constrained? And then this one is pinned, is a roller, and this one is free. So how many degrees of freedom do I have? Let's think about it. How many degrees of freedom I have? 3. What are the 3 degrees of freedom that we have here? This can move to the right, and this can move up. That's D1 and D2, and then this guy can move up or down. So that's D3. My stiffness matrix at the end has to be what? Of what size? 3 by 3. And I should be able to solve for D1, D2, and D3 with the applied loads I have. So let's look at the code number. The code number, which I gave it here, but let's say you don't, I'm not showing you that, and you just pretend that you're looking here, okay? Just focus here. What is the code number for element 1? So this direction is fixed, so that's 0. This direction is fixed, that's 0. So the first 2 numbers for code number for element 1 is 0, 0. And then for element 2, so for element 1, node 2, what I have? 1 and 2. So for element 1, I have 0, 0, 1, 2. For element 2, how did I decide to go about that one? From right to top or top to bottom? Which way did I decide? Top to bottom, right? So for that reason, I have to start here. So what is the code number for this direction? 0. What is the code number for that direction? 3. So I should have 0 and 3, hopefully, and I have that. And then for this guy, going to the right is 1, and going up is 2. So I have 1 and 2. And then finally, for element number 3, I think I'm boring you to death at this point, but we can still do it. How did I decide to go? Bottom to top or top to bottom? So I went from bottom to top, so then this is fixed in this direction, that direction. That's 0 and 0, code number 0 and 0. And this one is 0 and 3. So then I have 0, 0, 0, and 3. Any questions on this? Any questions on this? This is the moment to ask, because I will have another example.
So how do you decide the order of 1, 2, and 3 degrees of freedom?
Repeat your question
How
again.
do you decide 1, 2, and 3?
How do I decide 1, 2, and 3?
Node 2, if we're going horizontal, it's 1. If we're going vertical, it's 2.
So you can arbitrarily number everything as you want. The important thing is that when you define the element connectivity, you're consistent. I could have numbered it 1, 2, and 3. But the important thing is at the end of the day, you have control. You have to make sure that you're consistent. Okay? And I'll have another example with more truss elements. Trust me. We can look at that. Truss elements, trust me. That rhymes. Okay, so let's look at the stiffness matrix. I'm not going to bore you to death, but you can calculate the stiffness matrix for each of these guys, element 1, 2, and 3. Write the code numbers here. Bam. here, bam, here, bam. Now, assemble it. We said it would be 3 by 3, so 1, 2, and 3, 1, 2, and 3. Search for 1. Where does 1, 1 happen? So I look here. I do a search algorithm, and I look at where 1, 1 happens. Where does 1, 1 happen here? It's that one right there. And then here shows up here. And then here I have nothing. So those two will get added, and that's what you see there. I'm not going to bore you, but the rest of them can be quickly added up. Okay? And you can write a subroutine, basically, that'll automate this process. Okay? You want me to do another example of this, or you follow it, how I assembled it? Raise your hand if you want me to do another quick one. Okay. You want me to try one? Okay. Which one you want me to try from here?
Number 2.
So you want me to do 2 and 2 or 2 and 1? Let's do 2 and 1, something different. So 2 and 1. I'll go here. Where, do you see 2 and 1? Position 2 and 1. So position 2 and 1 is that guy, right? Do I see 2 and 1 here? So I search, I have a 2, and I have a 1 there. So that one has to be added up to that guy. Here, do I see a 2? No. And I don't see a 1. So I'm done. Those two need to be added, and that's what you see that are written here. Does that make sense? Okay, so I have assembled my the stiffness matrix. Let's look at the load vector, the force vector. The force vector, am I applying, let's go back to the original problem so you can see. In the original problem, in this direction I'm applying P squared root of 2 over 2. In this direction I'm applying P squared root of 2 over 2. In this direction I'm applying any force? I'm applying any force there? No. So it's 0, right? So then what I have now is my force vector. Okay? And so now all I have to do, well, I didn't do it, but K, this matrix, all these numbers are known. You agree? I have the deflection vector that needs to be solved for D1, D2, and D3, and equals the force. I invert the stiffness matrix, and I'll get D1, D2, and D3. I'll get the deflections. Okay? Any questions so far? Any questions so far on this?
So when you assemble the force one again?
Here, there's no reason. You're not assembling the force because, remember, we talked about applying concentrated forces. And so because of that reason, we're applying concentrated forces at this level, right? So at this level. The forces are not applied at the local element level. They're applied in the global element, in the global system, right? Now, remember, there is a difference here. In the homework problem number 1, there's a distributed force. I want you to go back to lecture 1, and I show you there how to deal with distributed forces. Those need to be tracked at the element level, and those need to be assembled. So let's look at that again, if possible, okay? All right, you're going to need it for problem number 1, all right? So let's look at another example. I think it's useful. I actually solved this in Abaqus as well, and I'll show you how I did it. This one is also in the book. So you have you can read it there also if you want to. But here I have the cantilever truss structure is fixed here, and that's the truss system. All the dimensions are given. The area is given here. The length of each bar is given here. And then you apply a load on the right-hand side, in the middle here. And so with this information, you should be able to now, basically, it's a great exam problem, actually. I mean, isn't it? It gives you all the information you need to actually execute. So in this problem, what I'm looking for is deflections, right? In real life, am I just looking for deflections? Huh? I want to know when the structure fails, whether it's safe or not. Deflection also can be an important consideration, but force, you need to also look at whether the structure fails. So that's the angle. In the problems I gave you, in both of them, I'm asking you to calculate the stresses as well and compare them to the allowable of the material. So moving on here, what I'm going to do, well, I'm showing you too much at once, but where do I have it fixed? here and here. So what code numbers will I assign here? 0 this way, 0 that way, 0 this way, 0 that way. So in the next line, what I show you is the element number, the way I've described it, 1, 2, 3, 4, 5, and 6. And then the other thing I've done, I put the code numbers here, 0, 0, 0, 0. For this node, I'm making it 1 and 2. But I could have made this one 1 and 2. I just, Arian, to answer your question, I just chose this way, okay? Which makes it really hard for we don't have a grader yet. I hope we get one. But it makes it hard for us to grade, right? There's a reason why I'm asking you to compare to Abaqus, right? It better be right. It needs to compare right, and it needs to compare to Abaqus really well, okay? 3 and 4, and then we'll make this 5 and 6. So how many degrees of freedom do you see here? 6. 6 degrees of freedom. It's kind of painful, right? Because you have to invert that, and I don't want anybody here to invert it by hand. You want to use MATLAB in that situation. Or Excel actually can invert things. Surprisingly, I didn't know it could do it. So for member one, what is the code number? Don't look at the solution is there, but focus on here. What is the code number? I start with node I, and that's node J. So the code number is 0012, and that's what you see there, 0012. And I chose this direction. You see these arrows? That's how I chose to start the element, from I to J, I to J, I to J, I to J. I'm choosing that direction, okay? You can choose any direction you want, but then when you calculate beta, you have to be consistent, okay? Beta is measured from I to J, the line that joins from I to J to the x-axis. That's how you measure beta, okay? So let's do another one. Element 6 goes from I to J here, so that's 3, 4, 5, 6. So that you have for element 6, 3, 4, 5, 6, okay? Anybody wants me to do another example? Well, you follow it. We're good? I like when you guys do this. This means I can go on, all right? That's great. So now I have a load applied here, a load applied there, great. All right, let's just keep moving on here. It's going to get boring from now on because it's really easy. Member one. So if I is here and J is here, how much is beta? 0. So beta is 0. EA over L is easy. The modulus of aluminum is 10 times 10 to the E6. But you see 10 to the E3 because we're doing everything in kips. So it's like in terms of thousands, okay? Area is given for each truss member, so you have that information. The length is given. Now, it's a trick problem because the length is given in feet, 12 feet, right? So I have to convert that into inches. So one thing I want to point out, I see a lot of errors being made in industry, and so you will see discrepancies. You have to convert everything to be in the same unit, okay? And I'll trick you in a homework and midterm exam because I want you to learn it. I want to make sure that you are aware. You're not just trying to mechanically solve something. You need to use your head and try to understand what you're doing, okay? And so from that perspective, we get K, the K. And if I substitute in my formula, in the formula that I had there earlier, where's the formula? This formula here, cosine of beta, sine beta, you put all this in, you will get for beta equals 0, that to be the stiffness matrix, okay? For that element, just for that element. And it's a good idea also to write the code numbers in here so that we had said that 0012, 0012, so that's what that is. For element 2 goes from here to here, right? Yes? And so how should beta be measured then? Beta should be measured between the x-axis, right, and that. Because we said this element goes from I to J that way. So beta is 143 if you calculated it using geometry. Again, the stiffness value K2 can be calculated, and you can quickly calculate the stiffness matrix. It's not difficult to do. I gave you the formula already. You can just use the formula, okay? Element 3, the same thing. I'm not going to bore you to death. 4, 5, 6. Okay? You can calculate all these things together. Then, what is the next step? What is the next step? I've calculated the stiffness matrices for every single element. What is the next step?
Assembly.
Assembly. Very well. So I'll assemble a stiffness matrix. That's my next step. And I tried to do it nicely here. And you can go home and verify it. Okay? But these are the code numbers. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If you want to know how I did it, it's very easy. Give me a number that you want me to go and search out. Give me a location here. Which one you want me to do? Arian, give me a location.
2 and 5.
What?
2 and 5.
2 and 5? Is that a good one? Yeah. 2 and 5 is great. It probably doesn't have anything. Good choice. Let's see if we have 2 and 5 here. Do you see a 2 and 5 here? No. 2 and 5 there? Yes, actually. And is what? 0. That location here. 2 and 5, that's 0. 2 and 5 here? No. 2 and 5 here? No. No. So you made a great choice. Anybody wants to try a different one?
Just a quick question. When we go through and we search for the locations for the codes, is there any reason why we choose the column number first?
I mean, you can look. You can do 3 and 4. You will get the same answer.
I just mean like, so, all right, so for 3 and 4 for that example, we go back to one that has 3 and 4.
Yeah. So the question for the video, the question is there any reason I chose a row or column first and then row? And the answer to the question is, as long as you get the position correctly, it doesn't matter. So the position I'm looking for is 3 and 4 as an example. And I'm going to search for that in the previous here. So I have 3 and 4. So that's that number. And in fact, it's symmetric, so it won't matter either. But that's why you see here I only wrote half of this because it's symmetric. Okay. Hopefully I didn't make a mistake. I don't think I did because 3 and 4 here, although you don't see that it matches what I had written, you have to multiply that by this number, and then you will get what I have there. Well, and it's not what I have there. It's actually an example from the book. Okay. I'll give credit where credit is due. All right. Now, all you have to do now is assemble the load vector. The next step is to assemble a load vector. And do I have, let's look at the loading that we have here in this example problem. Looking at this problem, what are the loads applied? I'm only applying a load here, and it goes with code number 6 and 2, locations 2 and 6. And they're actually acting opposite, so in a negative direction. Okay, and so if I go here, that's what I did. In positions 2, I put -9. In position 6, I put -6. Now I have my stiffness matrix. I have the deflection matrix. Sorry, stiffness matrix, load vector. What do I need to do now? Invert K and solve for the deflections. And I did that here in this, in this picture here. And when you solve for deflections, you get these numbers right here at the bottom. That's what you get. Okay. Any questions on that? Any questions on that? Moving on here. Let's say, okay, so now, are you done by just getting deflections? Are you done? But, I mean, we can go home because we calculated deflections. What else do I need to do? I want to know, in addition to knowing deflections, which is great to know, I want to know when the structure fails. Right? So then I need to calculate the forces in each member. Okay? To do that, I know the deflections. I know them. So what I'll do, I'll go to the local elements and calculate that information. So if I look here, remember, guys, that the local force was described as small f. Remember that? the local force, right? So let me go back and remind you that a little bit. So if I go to the diagram here, the big F was a global direction, the force in the global direction. I'm going to look at small f, which is, you see, the small f corresponds to the local direction. You see that? That's the one I'm interested in, because I'm interested in the force along the truss. And so we came up with the equation, I don't know if you recall, but we came up with the relationship of global force to, sorry, not global force, but forces in a local element in the global coordinate system, and then forces in the local element in the local coordinate system. We have a relationship there. So let's use that relationship to try to calculate the local forces in the system that I care about. I don't know where it went. Oh, here it is. So small f equals the transpose of the transformation matrix times f, big F, and then big F is K times D. I know this, right? And so T, the transformation matrix, is known, and all I have to do now is calculate that for every single element. So let's look at how I did that there. I know the transformation matrix for element number 1. I know K. I know the deflections. I calculated these numbers already. I got this earlier. So this was 0, 0, and then column numbers 1 and 2, D1, D2. This was the value for D1, that was the value for D2. So if I multiply all these things together, guess what I got? Look at the numbers I got. The force is 28 along here, and then 0 transverse. That makes sense. That's what I told you that we should be able to get before, because that's the assumption in this theory. So that's a great check, actually. If you don't get zeros, then you have a problem. The question is the membrane, member in tension or compression? So you can draw it, because we say FIX is 28. Okay, so that stays the same direction. FJX is minus 28. So we need to reverse that. So how is it acting? In compression. So that's how you know it's in compression or tension. Let's do one more example, because I don't want to bore you to death. It's the same formula over and over for every single member. For another member, we calculate the transformation matrix. We multiply by the stiffness matrix for that element in the global coordinate system times the deflections. And in this case, what do I have for element 2? For element 2, I'm here, and that's 1 and 2, 0 and 0. So I have the deflection D1, the deflection D2, and I have 0, and I have 0. And if I multiply all this together, guess what I get? I get 0 transverse to the truss. That's right. It should be 0. That's what we talked about. Because these members only carry load along the truss. And finally, I have minus 25 and 25. If I plot that here, minus 25 means I have to reverse the sign, or the orientation of that vector. And then 25 is acting that way. So that means in tension. And then I can repeat this process for every single member, and we've done that here for every single member. Okay. Now, to get the reaction forces, if I ask you to get the reaction forces here and here, the approach to do that, one approach, there's many different ways to do it, but the one approach that you could use is that you're going to take, you're going to actually, basically, remember I put here 0 and 0, 0 and 0, remember that? So let's just number those out, 7 and 8, 9 and 10. Let's just finish it up, okay? And then you'll assemble the full stiffness matrix with 7 and 8, 9 and 10 included, okay? And then when you multiply that by the deflection vector, okay, because these are all zeros, right? These D7, D8, D9, D10, the ones that go here are 0. The values are 0. I know these ones, D1 through D6, I know them from I just calculated them earlier. Just multiply these by that, and not only you can check that you should get 0 minus 9, 0, 0, 0 minus 6, but you will get these reaction forces. coming out automatically by this multiplication. Okay? Any questions on that? Because you're going to do this in the homework. I'm going to try not to be excessive. I don't want you to have a 10 by 10. I mean, I'm going to try to find, maybe we'll create a problem that's a little bit more doable, okay? But I think at the end you may need MATLAB or something to invert the matrix. You still need to do that. And if you do have questions on how to do that, you can email me or email him, Leonardo, and we can show you how to do the command in MATLAB. But I do recommend to get used to not having help, because in industry, you're kind of on your own. So you can ask help from colleagues, but there's something also called help manual. Okay? You can go to the help manual, and nowadays with YouTube, people show all kinds of things. So you can also learn there too, as well. That does not mean that we're not approachable. We'll help you if you ask for help, okay? All right, so how do I do this in Abaqus? How do I implement this in Abaqus? So in Abaqus, what I've done, and I'm not following that same numbering that I had over there in the example problem, but I'm solving the exact same problem. And so here, I've numbered the elements, 1, 2, 3, 4, 5, 6. So I've numbered them differently, I think. I don't think it's the same way. And then I have the non-numbers I'm numbering, 1, 2, 3, 4, and 5. That's how I did it. So, so what is the first step? Close your eyes, don't look. Well, you don't have to close your eyes. But I define the nodes. That's the first step. And so what I've done here is I put the node. How many nodes I have there? 5. I have 5 nodes. So I put 1, 2, 3, 4, 5, and I put the positions of each node, X and Y. Very simple. This actually took me literally. And I'm not trying to show off. It took me 3 minutes to put together. And it ran right the first time. And I think you guys can also accomplish that. All of you can do it really quick. It won't take long, as long as you learn the format. Now for element number 1, what is the connectivity? What nodes are connected to element 1? 1, 2. So that's what I wrote there. Element 1 is 1, 2. Let's choose element 4. Element 4, without looking, element 4 is connected by what nodes? 2, 5. And so element 4, I put 5, 2, but that's fine. It's going to work. And so forth. Okay, you can check the other ones. I did that.
So what is that type T2?
So thank you for asking that question. The question for the video is, what is type? And I forgot to mention what type is. But in Abaqus, there's an element library. And the element library gives you choices for what kinds of elements you can use. And the element that I'm using here is a truss element. Abaqus actually has a truss element. And since this is a 2D problem, what I've chosen to do is use T2D. So this T means truss, 2D means two-dimensional, and this 2 means it has 2 nodes. But Abaqus, in a manual, actually explains this to you also. In fact, just to be fair, I actually did not remember what element type I had to use because it's been a long time. So actually went to the Abaqus manual, clicked on element types. There's truss elements. So I clicked on truss elements, and then it told me what kind of truss elements exist. And I said, well, I want to replicate what's in this example problem. And I found that this is the one I want to use that will get me closer to the example problem. And so what I've done here, you can see here, normally, if everything was the same cross-section, same modulus, then you don't need to have everything in a different element set. You can have everything lined up back to back, okay? But because every single truss has a different cross-sectional area, I had to put them in different element sets, okay? That becomes important because I had to define that in here, in this section here. This section here defines the properties. Kind of like with the springs, remember I defined the nodes, the elements, and then I defined the properties of the spring. Remember that? Yes? So for trusses, similarly, I define the nodes, the elements, and the properties of that truss. So for element 1, solid section just means that I'm going to define the properties of that section. And if you look in the Abaqus manual, it tells you that for a truss, what you need to define here is the area, the cross-section area. It tells you what to define. Okay? For this particular problem, the cross-sectional area is 5.6 inch squared for element 1. For elements is 1.25, 0.4, 1.2, 1.6, and each of these is mapped to the appropriate element here. Okay, so the areas are mapped. Now I reference it also to the material, because in the property sections you have to also tell it what material you're going to be using. This is a made-up name. You know, I could put Leonardo. Material equals Leonardo, right? I can do that. But I put aluminum, Al. That's a short cut for aluminum, and then here I now define the material for that aluminum. So it's material, comma, name equals aluminum, star elastic. And under star elastic, I put the modulus and the Poisson ratio. The modulus of aluminum is 10e6, and then the Poisson ratio is 0.33. And then now I again start the solution sequence. Step static it's not a dynamic problem, so it's static. Boundary condition, so I'll apply the boundary condition now. What is the boundary condition? For node 1 and 4 is fixed. You agree? So for 1 and 4 is fixed. So degrees of freedom 1 through 6, I'm making them 0. This is fixed. Those nodes are fixed. All degrees of freedom are fixed for those nodes. So I did it, in reality it's a 2D problem, and you don't have to do that, but the degrees of freedom in Abaqus run 1 through 6. 1 through 3 are translations, okay, and 4 through 6 are rotations. And so although truss elements don't have rotations, I just fixed them. It's fixed anyway, right? So, but theoretically, all I had to do is maybe fix 1 through 2 and then 1 through 2. That's all I had to do. What are those applied? Yeah, the boundary. So just very easy. So the first number, the first column here is a node. The second one and the third one tells you the degrees of freedom. They need to be fixed. So if I look at the boundary condition for this problem, what is fixed? Node 1 and node 4, right? For node 1, degrees of freedom 1 through 6 is fixed to 0. And then for node 4, degrees of freedom 1 through 6 is fixed to 0. Does that make sense? Now I apply the external loads. C load, concentrated load. Where's the concentrated load applied? We talked about here, remember? We talked about applying it here and then here. In the original example problem, if you go back, oh, it's actually here. You can see there. It was 9 pounds downwards, 6.6 pound kips downwards in these two nodes. So let's go back to the problem, and I applied in node 2, right? Does that go in node 2? Right? So node 2, degree of freedom 2. The force is acting in the vertical direction, and that's degree of freedom 2 for that node. So that's 2 and how many pounds? Minus 9,000 pounds. And then for degree of freedom, for node 3, I have 6,000 pounds downwards. So I have node 3, comma 2, because degree of freedom 2, right? Minus 6,000 pounds, submit it into Abaqus. Abaqus solves it within like 0.01 seconds. I'm not kidding. All that effort I put, right? All these charts I was showing you. And then Abaqus just, bam, does it, right? Well, then, what is the next step, guys? What if this thing was deforming upwards? The whole thing was going up. What would you say?
There was an error.
There's a problem. Because I apply the load going downwards, I expect the whole thing to move downwards, right? So it's very important for you to check that things make sense, that things are really making sense. And also you can check other things, like the deflection should be the highest here, that makes sense. Anyway, you can check various, you can actually check that the deflection is 0 and 0 here, right? Well, what I did, I used something in Abaqus called probe values. I can probe the value at different locations. And what I did here, you can see, I probed the values at nodes 2, 3, and 5. So 2, 3, and 5. And I found the deflections there. So it tells me the deflection in the one direction and the two direction. So these are the numbers I'm getting, right? Now, if you compare this to what I got, was exact match. Like, I'm not kidding. It's like 0.288, 0.288. Right? So it's like perfect. Okay? And I was actually kind of concerned because I was putting this really quick together. And I'm like, if this doesn't work, I'm going to have to find the error, and this will suck. And it worked out. And I was like, yes, I'm done. I don't have to ask Leonardo to find the problem. Okay. All right. So there you go. No, actually, it will not have been Leonardo. It will have been you. I'll have asked you to find the problem. All right. So with that said, what I'm going to do, I'm going to give you a 3 to 5 minutes break. Actually, no, let's make it consistent here. So everybody has cell phone here. So be back by 5:20. I'm giving you 4 minutes to do whatever you need to do. All right? Okay. Now that you're back, I'm going to offer you an opportunity to make extra points as well. And one opportunity that you have here in this class is that you'll have the opportunity to program, and you'll get points for submitting a program that actually does what Abaqus just did. So if you develop a input file just like this one, and you write a program that takes this information and gets all the deflections, gets all the forces automatically, then you'll get extra points if you submit that. It needs to be well, explained. The code needs to be well explained. You should have a cover page for the report with explanations of how you went about it. Throughout the course, I'm going to offer these opportunities for various problems. For the Truss system, I'm offering the opportunity because it's a great way to start learning how to code stuff up. I give you some resources in my book on how to code these things with pseudo algorithms, and in the appendix I actually have MATLAB examples on things like that. I will not be able to have time to teach what's in the appendix, but I give you this opportunity because I think you guys are smart and you can do it. Many people in the past take upon this opportunity. When we approach the final, I'll also, no, actually, by next week I'll give you another opportunity that if this final report is so good, I may be able to say, hasta la vista, you don't need to do the final exam. So it depends. I'll offer that opportunity. That opportunity, only few will select because it's not easy to do. And I showed you a report from previous years. But I do ask that if you're going to work on this code, you work independently. Do not copy other people's work. You can corroborate. Now, my recommendation to you, collaboration means talking, trying to figure things out. But don't look at other people's code because at that moment in time, you'll be tempted to do a little more than just looking at the code. Just talk to each other. In terms of the help that Leonardo and I can provide for these codes, it may be a little bit limited because we're going to be focusing on what this class requires. But don't feel bad to ask me after class, like if, how I go about this, and maybe I can give you some clues. But generally speaking, it's pretty logical how to code these things up. As you saw, is the stiffness matrix the same for every single one of these elements, basically? The formula is the same. It's the same. The formula is the same for every single element. And to assemble it, as you can see, there's logic that goes along with that. It shouldn't be too hard to assemble it either. So I offer the opportunity for those that want to take it, okay? Yes?
So the code should be specific to a problem or can
No, the code has to work for any problem.
any number of elements?
Well, I'm not going to make your code work for 10 million degrees of freedom. It should at least work for 100, right? It should work for a large number of elements and nodes. I want to make sure it works, right? And not only that, you have to show that it works. So you have to run some examples with your code, and then you have to compare it with what you will get with Abaqus.
So the code need to graph the things or just
You can prepare tables with comparing Abaqus to whatever you think is necessary to validate your code. Deflections, forces, yeah? But I do want to warn you, I don't want you to put this as the highest priority. The highest priority is to finish the homework first, do that, do the CAE part of it, and if then you have extra time, because you have so much free time, code it up. And I recommend it. When I took the course, I did it, and for me it was not extra credit, it was required. And I learned a lot by doing it, okay? So I do recommend it. But I also know in a quarter system it's pretty tight. When I did it was a semester system, so I had more time. So for that reason, I'm making it optional, but strongly recommended. If you're going to pursue finite elements, as an area of expertise, strongly recommended. Okay, but with great reward, you get points, extra points. Okay, great. With that said, I'm going to move. Go ahead. You have a question?
Sorry, when do you want it done by?
I'm going to leave it a little open, so you have, 2 to 3 weeks to go about it. But the faster you do it, the more you can do, because as I move forward every week, I'll give you new opportunities, right? And so if you want to take advantage of every opportunity, you should start now. I mean, after you do the homework, and if you have the extra time, I recommend that pursue the opportunity, do it as quick as you can, so that when I give you the next opportunity, you can try that one. But I don't expect giving the next opportunity maybe in another 2 or 3 weeks. Okay? Great. There's no strict deadline. It's more at your own pace. Okay? Otherwise, if I give you a deadline, there's no motivation, right? The whole point I have is I want you to pursue the opportunity. Okay? But I also don't want you to give me a trust code at the very end of the quarter either. I mean, let's be reasonable here, okay? All right. Let's be reasonable. All right, so moving on here, I want to give an example of a situation that you could encounter in real life. And a situation is where this node, for example, can only slide on a slanted surface, okay? With a slanted surface along that's measured an angle alpha along the x-axis. So this is a rotor, and now I'm going to ask you a trick question. This is a trick question, a good exam question too. If I have made it fixed, do I need to worry about what I'm going to explain you next? If I draw the triangle, rotate it like that, and I make it totally fixed, do I care about what I'm going to say next? No, because it's fixed. So the deflection this way is 0, the deflection that way is 0. Okay? What makes this problem a little bit challenging is that all my loadings and boundary and deflections were converted into a global coordinate system. However, this rotor, it makes it difficult because it is an inclined surface, and now I have to somehow approach it, right? Because everything is a global coordinate system. The deflections are, the forces are, but yet the constraints I want to impose are easily imposed in a local coordinate system. So here you can see that. It would be easier if the coordinate system was this way, like perpendicular to this surface and along, because that way I can say, okay, perpendicular is 0 and along is free to go, right? I can do that right now easily in a global coordinate system. And for that reason, what we're going to do is we're going to use the following strategy. We're going to take that node, that particular node, and I'm going to actually, remember when it was fixed, I'll typically put 0, 0, right? Like here, 0, 0, and 0, 0. What I'm going to do this time around is a little bit different. I'm going to say, it's an inclined surface. There's actually additional constraints in some way because I have an inclined surface and that node can only slide along, right? And for that reason, I'm going to make it into degrees of freedom that are available, 5 and 6. I'm going to make it 5 and 6, although I know for a fact that that node does have a constraint, okay? But I'm going to make it available free, okay? And so I'm going to proceed the same way as I did before, assemble the whole thing with code numbers. And I'm not going to repeat this because it's the same approach. But what I'll do, and this is where the tricks come in, and I hope you can follow me. And if you don't, please ask me questions now. What I'll do, I'll transform. I'll transform 5 and 6 locally so that 5 prime is aligned with the slanted surface and 6 is perpendicular to the slanted surface. I'm going to do that. And if I write how D5 and D6 relate to D5 prime and D6 prime, I will use this equation, and you can check it at home, that this actually works out. So for 10 points extra credit, I want you to demonstrate that this is true, that this is a true thing, that this is going to work out, that that formula, transformation matrix, in fact, can rotate D5, D6 into D5 prime and D6 prime. And that's not very difficult to do because I already did it earlier in class, right? That's one of the things I did earlier in class. Similarly, the forces, the global forces can be rotated as well. So I have Q5 and Q6. I can rotate into Q5 prime and Q6 prime using the same transformation matrix. So I can use the same approach. And I'm going to call this transformation matrix TA. You can call it whatever you want. I'm just calling it TA for the purposes of this class. And the next thing I'm going to do, and please, when you see a lot of matrices like that, don't freak out. Let me guide you, and then you can freak out if you don't follow. Okay? In the equation at the top, that's the assembled stiffness matrix with the D1, D2, D3, D4, D5, D6, like before. I mean, basically the same thing as you had before. And the lows are 0, -9, 0, 0. Now, Q5 and Q6, you don't know what to do with them. So leave them like that for now, right? Because Q5 and Q6 are related to the situation here. I mean, that's Q5 and Q6. And I don't know how to quite address that right now. And I don't know how to quite address D5 and D6 either. For that reason, I'm going to take this and I'm going to think about what can I do. What I can do is to somehow make this D5 prime and D6 prime. That's what I can do. And make this Q5 prime and Q6 prime. If I can make that happen, then I know how to impose the boundary conditions. Then I know how to apply the global forces. So to accomplish that, I'm going to transform this vector D1, D2, D3, D4, D5, D6 into D1, D2, D3, D4, but with prime on D5 and D6 prime. And the only thing that will be affected is this guy here. Right? Can you see that everything works out? If I multiply this transformation matrix times that, I should be able to get the one on the left-hand side. So all I have done, I've augmented, and that's the word that we should be using, we've augmented this matrix into including the other degrees of freedom. So you can have them all there. Okay? I can do the same thing with the forces. So Q1, Q2, Q3, Q4, Q5, and Q6. Q5 and Q6 are the ones that are the ones I'm interested in having in the local coordinate system that is along the slanted surface. That's really what I want. Okay? Any questions on this? I'm going to give you like a minute to kind of digest a little bit. And then please raise your hand if you have a question. Because you will have a homework problem on this. So. Okay, no questions so far. So to assemble, you'll assemble it like normal, just like normal. And all we're doing here is trying to figure out what to do with these guys. And we're going to tackle it by transforming it so that these two guys, D5 prime and D6 prime, is in local coordinate system so that it's along the slanted surface and perpendicular to the slanted surface. Same thing with the forces, Q5 and Q6, Q5 prime and Q6 prime. Okay? I'll call this this variable here. Okay? And I'm going to use that. So moving here, you can see here that, you can see here that, let me call this D prime. Let me call this vector D prime. I'll call this that symbol. And then we call this D. Okay? We'll call this Q prime. And then lambda, right, I believe? And then you have this Q. So then I have this. I have D prime equals lambda D, Q prime lambda Q. Okay? And my goal, my real goal, is to somehow put things in terms of D prime and Q prime. If you see here, my stiffness matrix that I've assembled is K with the D's, and this D's is not the way I wanted it. And the Q. That Q, I need that so it follows that slanted surface. And so to do that, you can quickly see, I can calculate D very easily. I know D in terms of D prime because all I have to do is invert this. If I invert this, then I can get D. Now, the inverse of a transformation matrix is what? the transpose. So all I have to do is to transpose this to get transpose times d prime. I'm solving for d basically from that equation on the left. And then this is equal to q, right? Okay, now if I pre-multiply everything, this is a trick. If I pre-multiply everything by lambda here, then I get lambda on this side, I get lambda on this side, and guess what happens? Lambda times q is q prime. So I get q prime right there, and I'm done. Now I have been able to relate everything so that, and I'll show you in the next line. I'll show you in the next line. By using this technique, I'm now able to have d phi prime here, d6 prime, and for the q prime now I can impose the boundary conditions. You can see. So for d phi prime, what's happening? It's free to move, right? So is it unknown or known? Along d phi prime. It's unknown, I don't know. Along d6 prime, what is it? It's fixed. So I put a 0 here, right? And then q phi, because d phi prime is free to move on this direction, what is the load? There's no load that is being applied there, so that's 0. You can see how nice this is now, because I've transformed it, and you have to perform this operation, this lambda transpose times the stiffness matrix times this lambda. You have to perform that, of course. But after you're done performing that multiplication, everything becomes really easy now. Because what is the, how many, the only ones I don't know now is D1, D2, 3, 4, and 5. That's the only thing I don't know now. And so all I have to do is to solve the first 5 equations for D1, 2, 3, 4, 5 prime, and then use those equations to get this Q6 prime, this reaction force. Any questions on that? This is a little bit complex, I understand that. But like I said before, if you understand the process, that's really what matters. I want you to understand the process. That's really what I care about. But again, after this class, if I was you, I'll spend another hour trying to revisit what we've learned here. Otherwise, you will forget what was discussed here, okay? So I really recommend that. It will be of great value to you. Now, how do I do that in Abaqus? Because it's kind of fun to do things 2 ways. One, theoretically, and then, well, I don't know if you consider this fun, but it's a good opportunity to learn, right? And so the way to do this in Abaqus is the following. So how many nodes I have? I have 1, 2, 3, 4, 5. It's the same problem I gave you before, but the only difference is I'm not applying a downward force here anymore. I'm just applying, I want things to be inclined in a surface so that this node only moves inclined on that surface. So everything is the same. The only thing I'm going to do is create a node set. And a node set is just a fancy way of saying I'm going to name this node with a name. I'm going to give it a name. So node number three, node number 3, I'm going to call it skewed. So I call it n set, comma, n set equals skewed. That's the way you name that node and you give it a name. That's how you do that. So node 3, I wanted to give it a name, and I thought of the word skewed. I don't know why, but that's what I give. So skewed. So the next step is I want to transform. I want to transform the behavior of that node, n set equals skewed. So star transform, comma, n set equals skewed. What I'm going to do here is provide basically, and now I have to draw it here so you can see it. Hopefully this will show up in the video. So this is a global coordinate system, x and y. And what I'm providing this vector, x prime, and I'm providing that vector, y prime. So the first 3 numbers are providing x prime, the vector x prime, and the last 3 numbers are providing the vector y prime. In this case, it's 45 degree. I made a 45 degree slanted surface. And of course, if you know this, 0.707 is basically square root of 2 over 2. That's why you see that these numbers are the same. That makes sense, right? If it's 45 degrees, you expect the vector to be the same. The value is the same. And then here, that's the y prime vector. So in this example, now everything else is the same. Everything else is the same. Elements, solid section, everything is the same. The difference now is that the boundary conditions. That's where the difference is. Because, I mean, if I cannot transform it, it will be really hard to impose a boundary condition. I don't even know how you will do it in a smart way. So, start boundary, nodes 1 and 4, just like before, they're fixed. No difference there. Node 3, now the cool thing is I can make it fixed along perpendicular to the slanted surface. Perpendicular to the slanted surface is degree of freedom 2, right? Because along the slanted surface is 1, and then perpendicular to the slanted surface is 2. So degree of freedom 2 through 6, I made it 0. The only load I'm applying is minus 9,000 pounds here. I'm no longer applying, in this example I didn't apply a load here. This is an example to show you how to deal with a slanted surface. Any questions there?
So if you wanted,
I have multiple questions, so mention your name and then the question, please.
Bryce, so I was wondering if the direction 1 was constrained, or sorry,
Direction
2 was constrained, how would you code it? So you would have
But direction 2, so direction 2 of which node?
node 3.
But that is what is constrained in this example.
Okay, so if direction 1,
You want to constrain direction 1?
I'm just thinking for code, because you said 2 through 6, or sorry, 2 through 6 are constrained there. If you had, say, node, or directions 1 and then 3 through 6 constrained, how would you write the
So the
code?
question that you have for the video is that if this constraint, so instead of having this situation, you have this situation, I think is what you're asking,
Yeah.
right? So it rolls this way instead of that way, right? Is that the question?
Yeah.
Then you'll have to make sure that when you do the transformation, that you have it correct. You have to do the transformation correct for that. And then you apply the boundary condition in a similar fashion. I mean, it's no different. Arian.
So in the boundary, when you call in node 3, how come you don't call the skewed that you named?
Sorry?
How come you don't call the new
I could have put the word skewed. So the question for the video is how come I don't call it skewed later on? I can actually call it skewed here. I could have written the word skewed here.
Okay, but how does the code know that 3 doesn't refer before transformation?
The code knows that, so the question is, how does the code know that 3 is referred as skewed? Is that the question?
When you're calling 3 and you're saying direction 2 is fixed, how does code know direction 2 is not perpendicular to the x-axis?
Because we transformed node 3, right? We transformed node 3 to have a different coordinate system. So now it's x prime and y prime. So these are my degrees of freedom now, 1 and 2. These are my new orientations for degrees of freedom along x prime and y prime. Yeah? And Bryce, if you have, at the end of the class, I can give you another example. Because I think that will work better for the video and then us continuing with the class. So I only have a few more minutes to go, but I want to kind of finish what I have here today. I want to show another special case that you may have. And this is another area that I think we can take more advantage of in industry, and also as something I want to instill in you, is that it takes a long time to solve some of these problems because they're quite complex. And so it's important for you to find ways to simplify the problem in a way that you can make use of computational efficiency. For a problem this small, it doesn't probably matter. But for the purpose of learning, I think it's important for you to practice that. So your homework problem is going to have a symmetric boundary condition or something. So you can kind of practice that. But if I give you a problem like that, and clearly it looks symmetric, then instead of modeling the full truss system, just model half. Half, and then put a roller here and a roller here. Right? Because these nodes cannot move to the right. This node cannot move to the right. So therefore, you should have a roller there because it's symmetric, right? The second thing is that this middle truss, because I'm cutting the whole thing in half, I need to make sure that that truss is modeled as a half, half the cross-sectional area. Other than that, if I solve this problem, I'll get the same answer as the full problem. And it's very important, even for aircraft models. Aircraft models are typically modeled they only model half of it. A full 737 model only models half of that. I mean, why model the whole thing when you can just model half and get whatever you need to get? Okay. And if you're interested, at the end of the class, I can show you how they account for worst case scenarios like bank angle and other situations that are not symmetric. They have ways to account for that in a symmetric model. So that's a special case I want to show you. I want to also show you very quickly, very briefly, the homework is not going to have this. The book doesn't have it. I don't think either of the book has it, but I want to show you quickly how to extend this to 3D. So for 3D, again, same concept. I have a truss in 3D, X, Y, and Z, and it's the same formula as before. But now what I'm going to do is I'm going to use direction cosines to represent the behavior. So I have this del Jx, and I'm going to break it up into dJx, dJy, and dJz. And basically, how you relate del Jx to these d's, which are global, can be expressed in this manner. These are direction cosines, which can be calculated if you know the coordinates here, you know the coordinates here, then the cosine of theta x is basically the subtraction of the x direction of this guy and that guy divided by the length of that truss. That'll give you the cosine of theta x, and then so forth, cosine theta y, cosine theta z. So that'll give you that formula. Del Jx is the one, sorry, del Ix was the one here, and then del Jx is the one here at the top. But basically it's the same thing, right? Same formula. So because it's almost the same formula, I can put a matrix notation. So del Ix, del Jx, and I'll relate it to the vector, global vector, dix, diy, diz. Those three are for this corner here, I. And then djx, djy, djz. These three corresponds to the global deflections at j, not j. And do you agree that if I multiply this by that, I get these two equations? Look at it carefully. I'll give you 20 seconds. Can you see that the first row times this column gives me the first equation? The second row times this column gives me the second equation. Do you see that? Yeah. Let's call this T. This transformation matrix T, okay, 2 by 6. I'll call this D, vector D, and this del. Just like before. No difference. Let's now look at force. Same thing. With force, I'm going to take the local force that goes along the truss, and I'm going to decompose it into the three directions, okay, using the direction cosines. And I know the cosines from here, from these formulas. So I have that now. The relationship of local forces and global forces are basically, these are local forces. All these are local forces. These are represented in local coordinate system. These are represented in the global coordinate system. So I'm sorry if I'm saying global forces. It's not correct. Okay. So pardon me there. But if I multiply these by that, I get these two equations, and I'll call this F. I'll call this T, and I'll call this F. All right. Next step. F equals K times delta, and you know K prime. K prime was given here, right here. So that's F K times delta. That's this equation here. But I'll do everything in matrix notation so we can quickly do it. F equals K prime delta. Use this relationship. Del equals TD. F equals TF. So I put this one there on F, so TF. And then for delta, I'll put TD. So I get that. Now I solve for F by inverting this. And the inverse of T is T transpose. So that's why you see T transpose there. So now my stiffness matrix, global stiffness matrix for 3D problem is given by that. And now I've done the operation here for you. I have this times that, and I get a 6 by 6 matrix. Hopefully 6 by 6 because I have 6 degrees of freedom. Look at it. 1, 2, 3, and then I have the same ones here, 1, 2, and 3. So now the code numbers for a truss element in 3D goes 1 through 6, 1 through 6. In fact, if you write a code for 3D instead of 2D, I'll double the points. Okay? I'll double the points. Sorry? For the truss problem. If your code works for 3D, I'll double the points. Okay. Any questions so far? I'm almost done. 2 more minutes. I know it's been 2 hours, but that's how my classes go. The force equilibrium. Let me choose a row of forces, and I'll choose row I. So if I look at row I, K times D times F, and I'll look just row I. So I multiply it and I get that, right, for row I. I'm going to apply a unit displacement at degree of freedom J. And everything else 0. So when if everything else is 0, that's 0, that's 0, and then somewhere in between, whatever has J, that displacement I'm going to make it 1. So would you agree that everything else goes to 0 then, and I get Fi equals Kij? One more time. So if I look at a row on a stiffness matrix times D equals F, the deflection equals the force vector. If I multiply K times D, I will get F, right? I will choose row I, and I chose row I, generally speaking. Okay. Now what I'll do, I'll set degree of freedom J. So I'll set one of these guys, basically. One of them. I'll set it to 1. And everything else to 0. If I set degree of freedom J, somewhere in between, do you agree there's a Kij somewhere? Right? But everything else I'm setting to 0. So all those go to 0, that goes to 0. So I get Fi equals Kij. I get that. So the thing I want to explain here is that the physical significance of the stiffness matrix, particularly a component of the stiffness matrix, Kij, is that Kij is a force at degree of freedom I, so that's the degree of freedom I, because that's the row I selected, due to a unit deflection at degree of freedom J. Right? So degree of freedom J, I put it 1, while keeping all others to 0. This is another method to develop the stiffness matrix. You can actually do this also. You can develop the full stiffness matrix by doing this. And this method is used in civil engineering or structural analysis, structural matrix analysis. Coefficient of influence method uses something very similar. So I'm just trying to explain the physical significance of that. If you still have questions on this, we can discuss it at the end of the class. Okay? With that said, that's the last slide. So I've gone through 60 slides today, plus maybe other 20. So you have a lot of work to do. And I'm going to post the homework. I'm going to post the homework related to these trusses today. So you have 2 weeks, because you have a homework due next Thursday, right? So the homework related to this will be due not next Thursday, but the following Thursday. So you'll have plenty of time so that if you finish the spring homework, you can start working on this one. Okay? So that's my goal, is to keep moving along, and then hopefully you can, hopefully you have enough time to also have fun. It's important to also have fun outside of work, right, or class. So thank you very much for listening. You have a great weekend, and talk to you on Tuesday, all right? And I'll be here for another half hour or 1 hour, whatever time is needed to answer questions.